Section 3.1, we're going to be determining whether a relation is a function, much like we did in the last chapter, except for this time we're going to be working primarily with equations rather than sets of data. We're going to be finding the domain of functions, and we're going to be evaluating and graphing piecewise and greatest integer functions. So we're going to start out with the difference quotient problem. The difference quotient is something you're going to use a lot of algebra in, and see I'm missing a H here. You're going to use a lot of algebra, and it's something you're going to use in calculus as well, or something that you're going to find in calculus, but there's a lot of algebra involved in this. So rather than focusing right now, we're not focusing on the calculus part of it, but instead we're focusing on the algebra involved in simplifying the difference quotient. And so we're going to start out with just this basic problem here, where you've got s of x here, this function, and our final goal is to find the difference quotient, which is here. So in order to do that, what we're going to do is go through and find the s of x, which you'll notice the s of x is here, and then this, which is basically the entire piece, and then over h. So the h is the simple part. All right, so first of all, we're going to go ahead and do this. So what this means is to everywhere we have a variable in the original s of x, we're going to replace it with the x plus h. So I've got a 3, and I'm just going to use parentheses wherever I have the x for the variable, minus 2 parentheses. So this was my original, and it is now being replaced with the x plus h because we're finding s of x plus h. Okay, and now that we have that, we're just going to simplify. And when I simplify, I get 3 times, it's going to be x squared plus 2xh plus h squared minus 2x minus 2h. Okay. Now we distribute the 3, and we get 3x squared plus 6xh plus 3h squared minus 2x minus 2h. And then I continue to simplify here, and you notice that there are no terms here that can be combined, so we can actually just leave it like this, and that's fine. So we've got the 3x squared plus the 6xh minus the 2x minus the 2h, and then plus the 3h squared. So we're just going to leave it as this for now. So that's that expression. That's the first expression. And now that we have that, we're going to find the next expression. I'm going to move on to the next page. So this is the s of x plus h minus the s of x. All right, so we already know what the s of x is. And from the previous problems, we already know this. So I'm going to copy this. All right, here we go. So what we have here is this piece. All right, now we're going to say minus the s of x. So the key here is to use parentheses, and s of x is 3x squared minus 2x, and that negative is going to have to be distributed to here and here, and that's a point where people usually mess up. So we're going to go 3x squared plus the 6xh plus the 3h squared minus the 2x minus the 2h minus 3x squared and plus 2x. And now from here we're just combining like terms. So you've got the 3x squared and the negative 3x squared. They cancel each other out. You've got the negative 2x and the positive 2x that cancel each other out. So we're left with 2xh plus 3h squared minus 2h. Okay? And so, and again, it doesn't matter what order these expressions or what order these terms are in. So now that we have that, let's move on to the next one. And this time, this should have an h here. We're looking at the difference quotient. Now, the difference quotient is used to find the average rate of change. That's what it's used for. Right now and today in pre-calculus, we're just focusing on the algebra that's involved in simplifying this type of expression. So what we've done on the previous two is we have found this piece, and now we're going to divide by h. So if I go back to the previous, I'm just going to copy this. And here we have this. So as we know, this piece here is here. Okay? And now we're going to say divided by h. And when we do, every term there has a factor of h in it. So I'm going to divide everything by h, and I end up with 6x plus 3h minus 2. And the denominator would be 1, so I can get rid of my fraction bar here. Let's finish that 3. Okay, and so here we go. We have the expression. That's all we need, and that's the algebra involved with the difference quotient. All right, so now what we're going to do is look at some equations and determine whether or not they define y as a function of x. So we already know what a function is. It's a relation in which there's a one-to-one relationship, in which, I'm sorry, it's a relationship. It's a relation in which there's exactly one output for every input. It would pass the vertical line test. You know, if you have a repeat in the domain, then that's when there's going to be an issue with it being a function. So in this first example right here, you notice you have an x and a y in it. And what we're going to do is we're going to attempt to solve for y. So if we do that, we get 2y cubed equals 32x minus 11. All right, so I'm going to divide everything by 2 now. And I can do that individually if I want to, each term. Y cubed equals 32 over 2 is going to give me 16x minus 11 over 2. And now I have the y cubed, and I need to get rid of that y cubed. I want y, not y cubed, so I take the cube root. Okay, and when I take the cube root, then that's going to leave me with y is equal to the cube root of 16x minus 11 over 2. All right. Now, instead of answering the question right now of whether or not the equation defines y as a function of x, I'm first going to go through and solve for y in the second one so that we can compare these, and then we'll answer them both at the same time. So in this one, I'm going to move the 2x over and the 3, so I end up with y squared is negative 2x plus 3. And now I'm going to take the square root of both sides to get rid of the y squared. Now, when I take the square root of both sides, because I'm working with an even power here, what could happen is that, for example, let's say that I had negative 5 in there. Okay, these are both equivalent to this, okay? So when I take the square root of both sides, when we're working with squares, or when we're working with even exponents, I have to make sure I'm taking the positive and negative here, because it's going to produce two possibilities, the positive and the negative. When we're working with cube root, if we have something like negative 8 and we're looking for the cube root of that, well, we know the only thing it could be is negative 2 because it's a negative 8. So if it were a positive 2, then that would produce a positive 8 because 2 times 2 times 2 is 8. But negative 2 to the third power, on the other hand, is negative 8. So anytime we're working with even powers or taking the square root, fourth root, something like that, we have to use the positive and negative. Whereas if it's odd power, we do not. So this time we're left with y is equal to plus or minus square root negative 2x plus 3. So now let's move on to answer our question. The answer to the question is that yes, this does define a function, and no, this does not. And the reason being is because, first of all, if you were to look at a graph of this one, it's going to be something like, sort of like a parabola on its side, and it would not pass the vertical line test. And it's very easy to see is because, you know, each y value could be associated with is going to have two you have the positive and the negative there. So the answer to that question is no, because of the positive and the negative. Whereas when you're dealing with the cube root, it's only, this is, assumed to be a positive out here in the front. Okay, now we're going to determine, now we're going to look at the domain of a function. So for the square root of x, when x is greater than 0, if you have f of x divided by g of x and you're asked to find the domain, then we have to consider a couple of things. First of all, does the function contain a radical? And then the second thing to consider is, does the function have a variable in the denominator? So we want to know if it contains a radical or does it have a variable in the denominator. Those are the times when we're looking, when we have potential problems. So let's say, for example, I have f of x is equal to x plus 3. And I say, what's the domain of this? And you say, well, does it contain a radical? The answer is no, it doesn't contain a radical. Does it contain a variable in the denominator? No, it does not. So the domain to this is all real numbers. Okay? When it does contain a radical or it does contain a variable in the denominator, then we have to look at some other things and find its domain. So here are two examples. In the first one, we notice that we do have a problem. We don't have a radical, but we have a variable in the denominator. So you have to look at your denominator. And what do you know about the denominator of a fraction? You know that it cannot be equal to 0. So you use whatever that denominator is and set it equal to 0 or not equal to 0. So if we were to solve this, we'd subtract 4 from each side, and we know that x cannot equal -4. So the domain of this function is all real numbers except for -4. Written in interval notation, that would be from -infinity up to -4, not including -4, and then from -4 again to positive infinity. If you look at this on a number line, what we have going on is this is what we have. So it might be a little easier to understand here how I got this interval notation. Okay, and now let's look at our second example. This time we do not have a variable in the denominator, but we do have a variable in the radicand. And since we're dealing with a real number system, we want to make sure that this here is a positive number. So by saying it's a positive number or that it's 0. So what we want is for that value to be greater than or equal to 0. So we just set it greater than or equal to 0 and find out what values will work for this. So subtract 1 from both sides. Okay, and I get that. Now I need to divide both sides by -3. And once I divide both sides by -3, you notice that you need to remember the rule with inequalities. Anytime I divide by a negative and I have this is going to change. Okay, so that becomes W is less than or equal to 1/3. Okay, and so let's also look at this one on a number line. So if I'm on a number line, let's do 0, 1, 2, -1. All right, so all values less than or equal to 1/3. So 1/3 is around here, and it can be equal to 1/3. So we have a solid circle, and it's going this direction. So in interval notation, that's from -infinity up to 1/3, including 1/3. So we have a bracket there. Okay, so that's the basics for finding the domain of a function. And now we're going to look a little bit at piecewise functions. So here, a piecewise function is one whose rule includes several formulas. So as you can see the example here. And the formula for each piece of the function is applied to a certain value in the domain, and that's specified in the definition of the function. So here, and this should say f of x or h actually. Look, the name of this function is h of x. So it should be h of x is equal to, and this is it. So, you know, part of it is this if the domain is here, but the other part is here if the domain is less than 3. So when you're solving these, if we look at example A here, I'm asking you to find h of 0. Well, first of all, you have to find out where 0 lies. Is 0 greater than or equal to 4? No, it's not. Is 0 less than 3? Yes, it is. So that means that I'm going to use this here to define this. So I use the 2 times parenthesis plus 15. I use this equation here. I plug in my 0 and I find out that this is 15. Okay, so that's part A. And let's look at B now. So B is h of 3.5. So if I'm dealing with h of 3.5, then I need to find out where 3.5 is. Is 3.5 greater than or equal to 4? No, it is not. Is 3.5 less than 3? No, it is not. So this one is undefined. Okay. And now let's look at h of 5. Part C. All right. So if I'm finding h of 5, I look at 5, and is 5 greater than or equal to 4? Yes, it is. Is 5 less than 3? No, it's not. So we know we're dealing with the 3x squared minus 5. And I plug in the 5 here, and that's going to give me 70, the result. Okay, so I have those three. And then we want to know what is the domain. So if we're looking for the domain of this, if I just draw a number line, it might help me out a bit. So first of all, I've got 4 and I've got 3. So I'm going to start at 0 and go, let's do this. 0. Okay. All right, so for the first part, we've got x is greater than or equal to 4. So that's from here going this direction. And then we've got x is less than 3. So the domain of this function written in interval notation would be from negative infinity up to 3, not including 3, and then it picks back up again at 4, including 4, to positive infinity. And there we go. Next, we're going to look at graphing some of these piecewise functions. So I have an example here for you. All right, so since we have, it looks like what we have is a linear equation for part of it and then a quadratic for part of it. So what I would recommend doing is maybe working with two different t-tables on this and trying to graph from the two t-tables. So let's work with the first equation here. X and then the 2x minus 3. Well, we've got to find out what x values we can plug in. Well, x is less than 4 is what it says. So what I would do is start out with the 4, but it says it's less than 4. So I'm going to circle this right here because I know this is going to be an open circle in my graph because it doesn't contain the equals. I'm going to go 4 and then I'm going to go less than 4 because it says x is less than 4. So 4, 3, 2, 1. Just give myself a couple of values there. Now once I have those couple of values, then I'm plugging into the 2x minus 3. And so if x is 4, then we know that the y value here is going to be 5. And if x is 3, then we know it's going to be 3. And if it's 2, it's going to give me 1, and then 1, negative 1. All right, so I have that part. Let's go ahead and graph that. So again, we have an open circle, and let's use the red for that. So we have the point 4, 5. And so we got an open circle here. And then we have the point 3, 3. So the point 2, 1. And the point 1, negative 1. Okay, so it looks like what we have, and it's going to continue, and you probably need to note that this would continue here because its x is less than 4, so it would continue. So we have that part of the graph, and now let's come over and find the second part of the graph. This time we're dealing with x, where x is going to be between 4 and 7, including both of those. So let's just go all the way up, 4, 5, 6, and 7. And y value, or the output value, is going to be x minus 4 quantity squared minus 2. And if that's the case, if we input a 4, then I'm going to get negative 2. If we input a 5, we get negative 1. If we input a 6, we get 2. Input a 7, we get 7. Okay? And so now let's graph that. We have 4, negative 2, and 5, negative 1, 6, 2, and 7, 7. Okay, and you can see that it looks like it's a part of a parabola. So this is the graph of our piecewise function here. And a quick review of this, we have the open circle here at this point. We have the open circle there because of this. All right, it was excluding 4 from that part. All right. Now we're going to try to write an equation of a piecewise function. Okay, so this piecewise function looks like, to me, it has 1, 2, 3, 4 equations here to be dealt with. Okay, so I would start with that and start by numbering them and go ahead and get set up. And it doesn't matter what you call it. Let's say it's f of x. And we know we have 4 different equations going on here. And let's go ahead and define the domain. So for the first equation, it looks like I'm going from negative infinity up to where x is 0. Okay, so, or from 0 down to negative infinity. So this is going to be x is less than 0 here. Now it is a solid circle, so you need to decide whether this point here is going with equation 1 or equation 2. So we're going to let this go with equation 2. So we're just going to use the less than part here. So for the first one, we've got x is less than 0 for that first equation. And now let's go ahead and find the equation. Well, it's a horizontal line, and so we know the equation is y equals some number, or just f of x in this case. And what does f of x equal? Well, it looks like it equals 3 to me. So we have that. There's our first one is taken care of. Okay, now let's take care of our second one. All right, well, our second one looks like it picks up at that 0, and then it goes to right here, which is at 3. So from 0 to 3, x is between 0 and 3. We're going to let this include the 0 this time, as we said. And now this point here is contained by the second equation and the third equation. So we're going to let it go with the third equation this time, just like we did the first time around, letting that point here go with the second equation. Okay, so now we need to find the equation of this, this portion here. So to do that, to me it looks like it has a slope. Rise over run is up 1 over 1. So it looks like it has a slope of 1, and it looks like it has a y-intercept of 3. So that means that our equation is going to be f of x equals x plus 3. So that takes care of our second equation, x plus 3, when x is between 0 and 3. Okay. Now we're going to go through and find our third equation. Our third equation looks like it starts right here at 3 and it goes to 6. Okay, so x is between 3 and 6, and we're going to set it up basically the same as last time. Not including, I'm sorry, let's do this. Including the 3 and not including the 6. Okay, and so for that equation, again, we have a horizontal line. So it's just going to be f of x equals some number, and that number in this case looks like it is 6. So the height there is 6. So we have this equation from 3 up to 6. All right, now we have one more equation to take care of. And so this equation looks like it picks up at the x value of 6, and it goes to the x value of 9. So we're going from 6 to 9. X is between 6 and 9. And since it's the last equation, we're going to let this point be a part of that, so I have the equals here this time. Now, what I'm going to do this time is I'm going to say, okay, it contains these 2 points here, which those 2 points look like they are 6, 5. And it looks like it contains this point here, which is 9, 6. Okay, so it has those 2 points, and so that means the slope is going to be 6 minus 5 over 9 minus 6, which is 1/3. Okay, so we have a slope of 1/3. So just choose one of the 2 points, and we have the slope now. So y minus 5 equals our slope, x minus 6. And we simplify all of this, and we're going to get y is equal to x over 3 plus 3. Oh, sorry, this is a, let's do this. And I'm going to move over there. So it was right, y equals. Okay, so we have this equation, y equals x over 3 plus 3. And this time it's from 6 up to 9. Okay, and so there we have the equation of our piecewise function. All right, 2 more problems. We're going to talk about greatest integer. Probably have seen greatest integer a little bit in algebra 2, but the greatest integer function is defined as the greatest integer not greater than the integer that the value that we're given, not greater than x. The greatest integer not greater than x. So for example, if I were looking for this value, let's do this positive value first. Let's say I were doing this. Okay, the greatest integer not greater than 1.2 would be 1. Okay, or the greatest integer not greater than 5.5. What's the largest integer not larger than 5.5? And the answer would be 5 there. Looking at that on a number line makes it probably a little bit easier. So again, let's put this here. And let's just deal with okay, so the greatest integer not greater than 1.1. 1.1 is about right here. Okay, so if you look directly to the left of that, that tells you our answer is 1. Okay, now when you do this with negative values, it's a little bit confusing. So a lot of you might say, okay, well that's -1. Well, the answer to that is actually not -1. Let's look at it on a number line and you will understand. So if I go to -1.1, it's right there. Now, if I'm thinking the greatest integer not greater than 1.1, you move to the left and not to the right. Remember how I said previously that we go directly to the left of that and you see the answer. Well, if I move directly to the left of that this time, it's -2, not -1. So looking at those on a number line with negative numbers definitely makes it make more sense. So the answer is, for this one, you would get -2. All right, so all of that now, and let's talk about graphing them. So what happens is this is very similar to y equals x, okay? Y equals x has a slope of 1. You graph the line, and what happens is you connect the points, you get this, and here's our line, okay? That's what we get. Let's see, let me like this place. Here we go. All right, now my smartboard's having a little trouble here. Okay, you're gonna have to bear with me on the blinking here for a minute. If you're not, you may not be seeing the blinking actually. Um, so if I have this, this is my y equals x here. All right, now you notice what happened with the y equals x is that I continue to go up along the way. So if you plug in 1.1, the y value is 1.1. But when I was doing this with the greatest integer, if I plug in 1, I get 1. But if I plug in 1.1, I'm still going to get 1. All the way up to, here I'm still getting 1. Whereas if I were doing this with y equals x, then I'm getting 1, 1, 1.1, 1.9. And so that's why you see it gradually increasing here. So what's going to happen now that I have the greatest integer is that it's very similar, except for what's going to happen to, instead of the gradual increase, I have this going on. Because it's going to remain at 1. The y value is still going to remain at 1 as long as I'm less than 2. All right. So to graph this, y equals, to graph this parent greatest integer, then what I'm doing is first I need to fix this graph. All right. I would start out with a graph that looks just like I'm, 1, 1, 2, 2, 2, and so on. Just like I'm graphing the line y equals x. But now, when instead of connecting the points, what's happening is this. When I get up to, so for instance, if I plug in 1.1, I get 1. If I plug in 1.2, I get 1. If I plug in 1.9, I get 1. All the way up to when I get 2, then I jump up and I get 2. It's here. 2.1, 2.2, and I get 3, I jump up here. So these are holes in the graph here at the end, and it jumps up to the next level. And that continues. So that's the greatest integer function. All right, and then the next one is now the greatest integer plus 2. So this is just a simple transformation here. If I'm graphing the line y equals x plus 2, then I just shift that up, a vertical shift up 2. Same thing is going to happen here. The slope remains the same. So if I go up, I change my y-intercept to 2 this time. And so I'm still keeping the same slope. So there's my y-intercept, 1 over 1. Continue with this. And now I just do the greatest integer part of it. And we can cover this, talk about the values of the greatest integer in class a little more as well. Just be sure to ask questions if you need help. And there we have that greatest integer graph. Okay, and that's all I have for section 3.1.